Hello everybody, and welcome to these lectures on computer architecture. Let's take a look at the electronics behind the gates that we have been using so far. So what is this all about? How are we actually going to implement the gates and the logic in real world? How are we going to build a computer? So far we have only been doing some kind of mathematics, but let's now let's start building our computer. How does this work? Let me again take you back to the beginning of where we started, where we were. So we were having our logic was built actually on the Huntington postulates, and they used basically these three logic operations. That was NOT, AND, and OR. These were the three actually that we used, and we derived our entire logic on that. Well, I already promised you that actually the AND and OR gates, they are actually consisting of 6 transistors, while the NAND and NOR gates consist of 4 transistors. And I'm going to show you this now in a moment. So it would be preferable to use the NAND and NOR gates, and in fact we can build our entire logic on only NAND and NOR gates. We do not even need the NOT gate, as I will show. And finally, we also have seen that the XOR gate also comes in often quite handy, as we have seen. So these 6 gates are our basic components, our blocks of Lego, if you will, for building our computer. That is the NOT gate, the AND gate, OR gate, NAND gate, NOR gate, and exclusive OR gate. So what is this all based on? Well, you can base it on a lot of things, like Charles Babbage. He made a machine that was based actually on mechanics. But nowadays, I hope you agree, electronics has conquered the world, and we do everything in electronics. And specifically, we do everything in digital electronics. And digital electronics can implement all these gates. Well, you can use TTL transistors or TTL technology, that is transistor logic. But nowadays it's much more often used is CMOS technology, and that is complementary metal oxide semiconductors. That has the advantage, which I will show, is that it consumes very little power. So let's take a look. So the first thing is we have to know what are the basic transistors in CMOS technology. Well, that is the MOSFET, the metal oxide semiconductor field effect transistor. It's a mouthful, but actually not so complicated, especially for the informatics people. We just consider them as interrupters. So that means we have here a transistor that has basically 3 pins, and the pin from A to B either conducts 100% or it is completely open circuit, so it doesn't conduct at all. It's like a high resistor and doesn't conduct anything. It's like an interrupter. If you have a light switch, you can switch it on and off, and it depends on the third pin. That is what we call the input. So the transistor can be switched on or off, and we have 2 types of transistor. That is P channel, that conducts with holes, and N channel, that conducts with electrons. That you can even immediately forget if you're only into informatics. But the thing is that for a P channel you supply here a high voltage. Let's say you put here 5 volts, and you maybe put here 0 volts. So now to make the P channel conduct, we have to put the input pin close to here, what we call, actually this is called this is called the drain, and here we have the source. So to make it conduct, you have to make the input pin close to the drain, and then it starts conducting from here to here. Well, the electrons flow in the other direction, but for us it doesn't matter. You could make it conduct, and to switch it off you have to make the input pin close to the source. And to remind you where the source is, that is indicated with an arrow like here or like here, and it shows the flow of electrons. This one you can also completely forget, but the idea is to make it conduct, you have to put the voltage away from the source, away from the arrow. So let me erase this so that I can continue my narrative. So the P channel transistor, it conducts when you put it, the input, you make it actually a low voltage, and it switches off when you put the input high voltage, then it doesn't conduct. So I have put it here as just open circuit. For the N channel that conducts with electrons, it's the opposite. Here's your source, here's the source, and here is the drain. And here is the arrow again, so that means it indicates where the source is. Now to switch the N channel on, you have to make it into high voltage, namely away from the source. And to switch it off, you have to put it into low voltage, namely close to the source. Then it is switched off. So you get it? Well, you can always wind back if you didn't get it. Now let me then show how this is useful. Let me put this here on the side. Let me see if I can put it a little bit that people can still read it. I don't want to sit in front of it. And then let's see our first gate. That is then the NOT gate. So how does it work? It's complementary, meaning that you use both kinds of transistors. You use P-channel. That's this one here. Oh, I want to use red. P-channel, that is here, we call it QP, that is transistor P-channel called QP, and we have an N-channel transistor QN that conducts by electrons. And you can see here that the arrows are in opposite sides of the transistor. So now it's complementary, meaning that they have both types of transistors. So if I now put the input here that is connected to both inputs of both transistors. If I put this now high, let me put it here as 1, meaning that the voltage is close to this pin here. That means, remember, that this one will close and this one will open. So let me write it here. This one is open circuit, and this one is shorted, meaning now we have a conduction path from here to here. And this one, the other one, I can show it here, this one is actually disconnected. So as you can see, if we put 1 on the output, it has the 1 on the input, the output is shorted to ground, and this ground, of course, we will call 0. That's a logic 0. Now on the other hand, if we put low voltage on the input, if you put a 0 on the input, let me put it here, if you put a 0 on the input, this one, of course, will open circuit. This one will be open circuit. So if I put it in white, I want white, this one is sort of this path, this conduction path is gone. While on the other hand, we have opened this channel here. So we now have a path from here, from the drain voltage here. It's called DDD. It's a little bit inconsistent sometimes, but never mind. So we have a path here from what is a logic 1, that is the supply voltage 5 volts or whatever voltage you use, maybe 3.5 in modern computers. But never mind, the output now is directly shorted to the logic 1 and you get 1 at the output. So if I put 1 in the input, I get 0 at the output, and if I put 0 in the input, I get 1 at the output. So that is exactly what we wanted. If you want low at the input, you get high at the output, high at the input, low at the output. And if we attribute low voltage to 0 and high voltage to 1, we get this truth table. And as you have seen here, note here, there is never a short circuit. There is never a circuit from the supply voltage at 5 volts or 3.5 volts to ground or the logic 0. And that means there is never a high current going from one power supply to the other, and that means we don't have high power losses, and that is why complementary CMOS technology, or complementary MOS technology I should say, is favored, because it doesn't consume very much energy, and that is of course what we want. We want a lot of computation power and very little energy consumption. So this is now how the NOT gate works. Let's see if we can find here another one. Now we can do the NAND. Okay, the NAND, as you can see, 4 transistors, 2 P-type transistors, P-channel transistors, and 2 N-channel transistors. Now imagine if I put here a 0 here and a 0 here. 0 here, 0 here means this one is not conducting and this one is conducting. So we get here a path out. And this one actually, because of this B input continues here. This one is on 0, means this one is not conducting. I'm sorry, this one is also conducting, and we also have a path here. So you have a double path to out. This one now, actually, it doesn't matter because it doesn't anyway conduct here to ground. So what do we get? 0, 0 input, and we get a 1 in the output. Now if I then, for instance, put B here a 1, this one starts conducting. This one starts conducting. That's nice. This one actually is not conducting because it's N-type transistor. This one actually is conducting, and this one is now not conducting. So what do we have? From out we don't have a path to ground, to 0, but we still have a path to 1. So 0, 1 also gives me an output high. And I hope you trust me that if you do the other way around, it also has logic 1. Now the 1 is when I put here 1, 1. If I put 1, 1, let's see, this one is conducting indeed. Transistor is conducting. This one is also conducting. This one is now has close to the source here, is not conducting, and this one, let me see, it's connected here, is also not conducting. So what do we have? We have a path from the output short circuit to ground to logic 0, and the 0 of the 0 power supply appears at the output. And again, we don't have a short circuit from the positive power supply to the negative, to the low power supply. But anyway, in this case that you put logic 1 on both inputs, or 2 times high, the output is low, is a logic 0, as you can see. This is then how a NAND gate works. For a NOR gate, let me see, where do I have it? That's number 5. I have it prepared here. Very similar, 4 transistors, and you get this kind of logic that is, oh, I want red. You get this kind of logic that is here, that the output is 1 for the input combination 0, 0. If not, it is 0. Let me show you here. If I put here 0 and if I put here 0, why is that doing like this? I have no idea. 0. So 0, this one is not conducting. This one from B, I put 0 here. This one is also not conducting. This one is a P channel, so this one is conducting because of this voltage here, and this voltage actually makes also P channel transistor A conducting. So we have the output here, the output that is shorted to the high voltage, and you get this when high 0, 0 in the input, we get sorry, that's not this one, it's this one. When I have low at the input, 0, 0 at the input, we get 1 at the output. And just to give you one more example, let's do here, let's put here 1 and let's put here 0. If I put 0 here, this one receives the input voltage from A, it's not conducting, but B, now actually this one is conducting here because B is high voltage, and that opens the N-channel transistor. So we have here a short to output, and this one actually, the B, it closes this one because it's a P-channel transistor, and that closes when the voltage is close to this supply voltage. And this one actually opens this one, that's okay. It opens this one, but it doesn't matter because the continuing transistor is closed, so there is no short circuit from the high voltage to output, nor to the ground to here to the 0 voltage. So 1, 0 at the input, we get actually 0 at the output. Let me see, B equals to 1, A equals to 0, that is this one, we get 0 at the output. And the other combinations you can check for yourself if you want. Just rewind the video, pause the video, and make this analysis yourself. You will find that actually we have this truth table, or in physics we have this voltage table, and that implements of course the NOR gate. So as you can see, 1, 2, 3, 4 transistors for the NOR gate, which we already had 4 transistors also for the NAND gate. Now then, how do we make AND and OR gates? That is funny, because you would expect them to be simpler, but in fact they are more complicated. What do we have? An AND gate is simply a NAND gate, that is this symbol, plus an inverter at the end. So that is 4 times 4 transistors here and 2 transistors here, that is 6. An AND gate has 6 transistors. So it has this funny structure with the 4 transistors and this inverter, the NOT gate with the 2 transistors, that's 6. The same with OR, it is a NOR gate, which is 4 transistors, plus an inverter, a NOT gate, which is 2 transistors, a total of 6. So if we can use NAND gates and NOR gates, that is preferred over AND gates and OR gates, even if the logic, as we learned from Aristotle, is easier to do with AND and OR. Actually, nature prefers NAND and NOR, so if we can do NAND and NOR, we will save transistors. Finally, the last I want to talk to you about, this is like a little bit a complicated beast, is the XOR. The XOR, I need a little to write. Let's use it here. Let me not sit in front of it. Let's see this one. Remember, how did we make an XOR gate? That was, it had this truth table. I want a little bit bigger here. This truth table is this one. So what are we going to do? Sum of products. That was A not B, A and not B, or not A and B. So what did we have? We had this AND, here we had not A, here we had not B, and then this one went to here, and this one also went to here. So that is, this top one is not A, B, and B, and this one is A and not B, and then we made them into an OR gate. I cannot write so well. So this was then the implementation sum of products. 2 AND gates and an OR gate, and remember this we could convert by de Morgan's law into let me put an AND gate, and here another AND gate, a NAND gate, sorry, this is NAND, this is NAND, I think I'm sitting in front of it, this is NAND and this is NAND, and then we have here A, B, and then not, and this one goes here and this one goes here the same. So what do we have now? We have actually we came then up with this structure that I have shown here. So we have here this one AND gate, NAND gate, another NAND gate, and another NAND gate. That is by converting the sum of products by de Morgan's law into 3 NAND gates. And we have here now these 2 inverters in the input to get the total of, let me count, this is 4 transistors, this is 4 transistors, this is 4 transistors, and this is 2, and this is 2. So we get a total of 16 transistors. And normally then in literature, what are they doing? They present it like this. I have to erase here everything. We get, normally in literature, you get this one, and these 2 are actually equivalent. Let me show this here. I don't want to block anything. So for instance, what do we have at this point? This red point. We have here, now let me first put it here, this X, let me put here an X, X equals A and B not. And then at this point, let's call it Y, is then this A and B not and A, and then everything inverted. And this, actually, Morgan's law, the negation of a product is a sum of negations, is A and B not, or A, not, and that is A and B, or not A. I want to write it the other way around because otherwise you don't get it. So that is not A or A or B. Just a negation of a negation is a negation. Not is true. But this one, this funny distributive law, this actually is A or not A or A, or not A. Sorry, I should not make mistakes. A, not A or B, and not A or B. That is the funny distributive law about the Huntington postulates. Just look back at it if you forget how this works. And this one, of course, this is 1 and not A or B. And that is exactly the same thing as what we have here, not A or B. So that basically summarizes it. I want to finish with this table to say to you that the number of transistors needed for a NOT gate is 2, for a NAND gate is 4, for a NOR gate is also 4, an AND gate is an AND gate plus a NAND gate plus a NOT, so that's 6. An OR gate is a NOR gate plus a NOT, and that's then also 6. And the exclusive OR gate is 16 in any configuration. So also this one, as you can see, is 4 times a NAND gate, and that is then 16. Finally, one small thingy, which has some philosophical consequences, that if you want to have the NOT gate, I want to read. If you want to have the NOT gate, actually it can be made of a NAND gate or a NOR gate, because, as you will see, NOT A, actually, remember the idempotency of the operation OR and AND. So NOT A is equal to not, I should put it in brackets, not in brackets A equals in brackets A and A not, because A and A equals to A, and in the same way you can also say that not, no, I want to put it differently, not A equals not A or A, because A or A equals A. That means that not A or A is actually not A, and not A and A is actually also not A. This in case if you want to also get rid of the NOT gate, and you can actually build any logic on simply only NAND gates and NOR gates. Okay. And actually only on the NAND gates then, remember, with the sum of products and with the products of sum. Okay, hope you enjoyed this lecture. See you in the next one.